give me the second greatest version of this mixing, this turbulent flow action.
Okay, so a simple way to look at turbulent reacting flows and its challenges are as follows. We have a fuel and oxidizer being injected. Those are mixing at what we call the energetic scales. Those energetic scales are relatively larger than the scales at which combustion occurs, which for our systems we consider the smallest scales in the flow. So let me kind of give you an example of how that works. So everyone's seen a plume coming out of a smokestack or any kind of industrial process where you see swirling flow and a lot of what we call eddies. And the eddies are turbulent eddies. And then the swirling flow is really the essence of turbulence. It's turbulence and the mechanism of what we call turbulence that's creating those eddies you can see. So what's interesting about reacting flows is we're mixing the fuel, which could be gasoline you use in your car, an oxidizer, which would be air. They're mixing at these larger energetic scales in a way that has to then interact with combustion. And the way it interacts with combustion, if you look at some of the flow images that we provide just to understand what's going on, what you see is a lot of kind of stringy, spaghetti-like structures. And the mixing is actually occurring within those structures, and that's where combustion has to take place. As combustion takes place, then it in turn affects how that mixing occurs. So there's kind of a feedback going on where, one set of processes at these energetic scales is affecting how the chemistry occurs, and at the same time, because from the chemistry, in our case, we have heat addition, that's changing the flow. And from there, when I say nonlinear, that just means one thing's affecting another in ways that can be very much amplified or damped.
Okay, let's cut that one there.
Yeah.
Let's move on to. Let's get us back to simulations. So you have this overarching work that is with all these different kinds of engines and turbulent flow, but there's a specific problem that you're bringing to Summit. Could you tell us what part of that you're going to be working on?
The problem we focused on initially and targeted Summit as the main platform for is something we've been working on for a long time, but really requires kind of the maximum or always the pushing the limits of the computer power we can get. In all of the devices we look at, many of the devices are now in high-pressure regimes where fuel and or oxidizer, in the case of liquid rockets, are being injected at supercritical conditions. From a science perspective, that just means there's something called the critical point, the critical temperature and pressure. That's from thermodynamics. And once you're above those two conditions, or in particular, you're at the critical pressure, we have something called supercritical fluid phenomena where, for example, if you're spraying your garden hose, you're used to seeing drops and those types of things, the water breaking up into drops. If I were to spray that garden hose at 100 atmospheres, where the water would now be being injected as a supercritical fluid, you wouldn't see drops. You would see kind of a very diffuse, misty type of jet. And that's what we call supercritical fluid phenomena, where under certain conditions, the fluid is behaving like a liquid, but at the same time, it behaves like a gas. So the problem we brought to Summit is precisely that problem, where we're trying to understand issues related to turbulent mixing in the context of supercritical fluids and its impact on combustion.
In any particular kind of machine? It turns out that supercritical fluids and focusing on those is important for many applications, especially high-performance applications. The leading example, of course, is in a liquid rocket, where the fuel and or oxidizer are always injected somewhere in the cycle at supercritical conditions. So that's one of the leading focal points and reasons to look at this research. But it turns out that both in
devices such as a diesel engine, where the compression ratios are very high, and also in certain modes that a gas turbine, so a aircraft engine burns at, or the afterburner in a military jet, can achieve pressures that require we understand supercritical fluid phenomena. So from the perspective of high performance, as I like to put it, power and propulsion devices, supercritical fluid phenomena is a fairly wide topic of interest, and there's still many questions that are in front of us to be answered.
So you'll be building a simulation of that phenomena using Summit?
That's exactly. So what we, yes. Let's see.
You can just tell me that in
okay.
a single sentence.
So we'll be, so our motivation, okay. So our focal point on Summit right now is supercritical fluids. Well, okay.
Oh, that's good. That's fine if you want to take a breath.
No, I'm just.
And I'm looking for that word simulation somehow. I think the audience needs to know. They understand that you're researching that phenomenon, but what is it you're going to make or come out with? And if my understanding is correct, it's a simulation from which other things can
right.
happen.
Our focal point on Summit is really looking at the details of supercritical fluid phenomena as it relates to propulsion and power devices, but with emphasis on two things. First is we need to start improving the databases available so we can understand how to best model some of these processes. So one of our first simulations on Summit right now is aimed at that precise task, is to come up with a nice fundamental data set that we can understand a lot of turbulence quantities that we're typically interested in that relate back to this whole thing of mixing and how that mixing affects the combustion process. Of course, the second thing then is, in kind of a workflow, if you will, is to understand how to take that knowledge, combine it with some key experimental efforts that are going on, and collectively develop and validate models that give us a better predictive capability than we have now.
And you don't have the previously not so, I don't know how to say this, the predictiveness that we have now. There's an uncertainty in there. Is that correct? There's just some things that you're kind of estimating currently that when you work on the problem with Summit, that you may have to estimate less and have a little more accuracy?
Yeah, so the current state of the art with modeling, turbulent reactant flow in general, but especially as you move to more exotic conditions such as supercritical fluids, the number of uncertainties associated with these calculations limits what I will say their predictive usefulness. That's to some degree always going to be the case. Turbulent combustion is not a problem where, ultimately, the ultimate brute force solution is just solving our equations on the computer where we resolve all the scales of the flow and those types of things. And even if we could, there's a compelling reason not to do that, but to still be innovative, because the more we can model predictably, that relaxes the demand for computational power. Ultimately, what you want to take is simulations such as what we do on Summit and use those to understand how to devise engineering models that, if we could, run on a workstation or something that industry can run very quickly and reliably, and a wider audience in terms of engineers, researchers, and scientists can use those models to move on and study other things like optimizing systems and those types of things.
And that's where the ideas of being able to reduce emissions or run more fuel efficiently come in?
Exactly. If we can get, interestingly, right now, when we talk about these devices, computers are certainly used to design these devices, but that's not all that's used. There's a lot of cut and try, we say, experimentation, and those types of things. And obviously, the goal is not to replace those, because all those things are invaluable. But if we can improve the predictive capability of the simulations, there's much more that can be done in terms of optimizing key features of these systems that we're interested in.
And that will give us
we're going to get improved fuel economy, reduced emissions. Ultimately, as we start experimenting with different fuels where we can manipulate levels of CO2 that are come as a product of combustion, certainly we want to minimize those types of things. There are cycles aimed specifically, thermodynamic cycles aimed specifically at essentially zero CO2 emissions, where we're separating those out, and all of those things can be optimized, and I think advances could be made much quicker if we have the added benefit of, say, a computational tool that can do wide-ranging parametrics and those types of things. A big difference in the simulations we do right now that are aimed at developing these models and simulations that would be done that are aimed at using a predictive capability is really in what one of them is in parametrics. So, for example, if I have a tool that I think is I can quantify the uncertainty and it has an acceptable level of uncertainty, in other words, the error bounds I would put on anything I'm interested in. If I can get to that point, then I can actually move into a design optimization type of mode where I can do thousands, perhaps, of calculations, and typically that's what's required when you start talking optimization. And you can let the computers help find the sweet spots in these highly nonlinear systems. And all nonlinear means is it's not straightforward. Just because you see a trend doesn't mean you're going to keep seeing that trend. As you move over some parameter space, any trend you're seeing in terms of, let's say, an improvement could significantly change all of a sudden if you move beyond a certain point. And that's a simple example of what I mean when I say nonlinear.